So these are the second two questions from the Step 3 Calculus Support Booklet. There's a really short one here, which is very similar to Gable's horn, actually. It's quite a nice question and quite easy as well. And then we've got a question about reduction formulas here to do as well. So let's start with this one here. We're being asked to find the area between this, the x-axis, and between 1 and a. So that's just the integral of y dx between 1 and a, right? So y is log x over x. I'm going to write that as 1 over x log x. Because it's just an integrating trick, right? It's f dashed of x now times f of x. So this just integrates to log of x all squared, and then you just have to bring the half out to make it all balance out. So that's quite nice. You can use a substitution and you get it just as well. But anyway, now we put the a and the 1 in. Now log of 1 is 0, so that goes away, and we end up with this. And now we're being asked to think about what happens to that as a tends towards infinity. So let's think about the limit of that as a tends towards infinity. Well, a log of infinity is infinity. It gets there very slowly, but it does get there. So this area tends towards infinity as a does. So that's kind of cool. Next part of the question is what happens when you do a volume of revolution of this same thing. So of course that's going to be the integral of pi times y squared dx between the same two bounds. Y squared is log of x all squared over x squared, which I'm actually going to write as x to the power minus 2. I chose to do this with integration by parts. It's up to you. There's probably other ways of doing it as well. But parts seem to work quite nicely because when you differentiate log, you end up getting 1 over x back. So it kind of goes quite nicely. So integrate this one both times. You get minus x to the minus 1. So I'm going to integrate that. I'm also going to ignore the limits for now. I'm just going to say, let's focus on this integral here without the limits and without the pi. And let's just do it. Integration by parts. Integrate that to get this and this. Leave this one alone there and then differentiate it over here. So that's going to be 2 log of x to the power 1 and then differentiate log of x to get 1 over x and just put the minus integral between. I don't usually set up the du dx thing. I just kind of write it all out. Integrate this a couple of times, leave that alone for there, and then differentiate it over there, put the minus integral in between. People who have watched my videos on integration know that I do that. Anyway, we end up with this because these x's come together there. The 2 come out the end, the minuses cancel, and this seems easier to integrate. We can just do the same thing again, I think. I don't see why that wouldn't work, because if we do the same thing again, based on the fact that log of x squared became log of x, I think it will go away in the end, and it does. And you end up with this eventually. There's our integral. So just doing parts a couple of times, nothing too tricky there. We can now know that, now that we know that this is the integral here of this thing, we can just put that result into here and evaluate between a and 1, which is this here. And yeah, put the a in, put the 1 in for all of our x's, and we end up with this thing here. These log of 1s go away because log of 1 is 0, so we just end up with a minus minus 2, which is just a plus 2, and we end up with this as our, sorry, I don't know what my buttons were doing there. This ends up with this being our volume here. And now again, it asks us to think about what happens to v as a tends towards infinity. So what I decided to say here was that, okay, we can take the limit of all of these things separately, which I will do in a second. However, of course, if we're taking the limit of log of a all squared over a, does that tend to infinity because or does it tend to 1 or does it tend to 0, right? Like, if you put in infinity, you get essentially infinity squared over infinity. So maybe that tends to infinity, or maybe it just cancels, tends to 1. Maybe it tends to 0 because this rises much quicker than this thing here. I evaluated it using L'Hopital's. A lot of people might just know that this goes to 0 because log rises so much slower than just a regular function a. But L'Hopital's works quite easily here. This is just from the FP1 book. The limit as x tends to some number of f over g is f dashed over g dashed, as long as that first limit either essentially evaluates to 0 over 0 or some kind of infinity over infinity, right? In this case, it does, right? As a goes towards infinity, this evaluates to infinity over infinity. So that means L'Hopital's will hold, and it will also hold for this one here, which is also infinity over infinity. And this, of course, when a goes to infinity, is just 0. So I don't need to use it on this one here. So that will just go to 0. This will obviously just go to 2 because it is just 2. The pi is irrelevant, bring it out to the front. These two are the key ones. So differentiating them both, I guess, separately. So this differentiates to 2 log of a times 1 over a, and a differentiates to 1. And this differentiates to 1 over a, and a differentiates to 1. And these limits should be the same because I've checked that they both go to infinity over infinity. Of course, this is just log of a over a with a 2 that can be brought out, and this is just 1 over a. But we know 1 over a already, we know that that tends to 0 as a tends to infinity. And we also know, based on working back a step, that this one, because I've just said so, this one tends to 0 as a tends to infinity. So does this. Or just do L'Hopital's again, because you're allowed to use it as many times as you want, and you show that both these things go to 0, I guess, and you just end up with 2 pi as your limit. And what this question is kind of getting at is that Somehow in the 2D scenario here, the area was infinite, but then the moment you revolve it around the x-axis, the volume becomes finite, which is interesting. And it's to do with a thing called Gabriel's horn, I think it's called, which is another version of this same question. Which you can look up if you're interested, or if you would be interested in doing so. And the last thing that I wanted to note about this question is that if you didn't know L'Hopital's, the other way the mark scheme actually gave to do this was you could have made the substitution not just for integration, but also for evaluating limits sometimes. So we can make the substitution as a tends towards infinity, so does b, because we end up with infinity over here. So you would need to use infinity up here to make this work, or you take log of both sides and you get log of a equals b, as a tends to infinity, so does b. Anyway, so then you can replace these. Log of e to the b, though, of course, is just b. And so we're evaluating this, and we can use the definition of e to the b being the infinite polynomial, the Taylor series here, and then just cancel all the b's, and then it's pretty clear that, well, that goes to 0, this goes to infinity, so you're doing 1 divided by infinity, which is 0, and the whole thing tends to 0 anyway. So that would be the other way of evaluating it, just as a quick note. Anyway, now we get to the reduction formula question. So let's start from the very top by considering the greatest value for this in this region. So, okay, greatest value, I decided to set it equal to a function f of t and then differentiate. You can write it like this and then use product rule. I thought might be the easiest way of doing it. Probably not, but whatever. Let's set that to 0 to try and find a turning point. Of course, if you times everything by t to the 1 all squared, you end up with this, and then there are no solutions to that because the t's cancel. So this doesn't actually have any turning points. Which means all we have to do to find its maximum point between 0 and 1 is just evaluate it at 0 and then evaluate it at 1 and see which one is bigger, because essentially it's just a function that's either always getting bigger or always getting smaller because it's got no turning points. So it turns out that it's just always getting bigger in this range, and its greatest value is a half. Okay, so the next thing that we'll have a think about then, I guess, is that show that this thing here. So firstly, we need to think about in plus 1. So just replace these with n plus 1s, you get this. And now what we can do, and think about how you're supposed to use the result you just had, I guess, because it's what it's telling you to do. How can we use this here? Well, we can factorize out t and factorize out t plus 1 to make ourselves this object here in the front. And we've just shown that this thing here is definitely less than or equal to half everywhere between 0 and 1, which are all the places we care about because that's where between where we're integrating from. So this thing here is definitely less than half in this thing. So we can just replace this with a half, and that will make the entire integral bigger, because like for values around 0, this is even less than a half, but it's most as a half. So if we replace it with a half, we're just making the whole thing, we're just shoving the whole thing up to a half, I guess, in this range everywhere, and so the whole integral is becoming bigger. But anyway, in this case, we can of course just bring out the half, and of course the rest of it is just in, because that's what you're left with, and so you have in plus 1 is less than a half in. So that's the first thing, just done and dusted. Show also that this thing here is true. So okay, now we're going to actually have to think about what in plus 1 is again, but do this slightly differently. We can't just do what we just did, because then we'll end up with this thing again. Now I think we should just think about doing the integral with reduction formulas or with some other kind of idea. And I just decided to do integration by parts because that's what you almost always do when you get these kind of integrals and reduction formulas, is you just do integration by parts. So I've decided to write this as a product, just use a minus in this power to make it go to the top row. And now I'm going to integrate this one here, because that raises this power. This power is currently minus n minus 1. So it would raise it up to a minus n, like it would make it bigger. And of course, getting it to a minus n relates it to the in. And likewise, if I differentiate this one, that brings it down to a tn minus 1. So I'm going to try and do integration by parts the right way around, such that I get something that looks a bit like in back, because of course I need an in from there. So okay, I did exactly that. I left this one alone, and then I differentiated it over here, and then I integrated this a couple of times, raise it up to a minus n, and then divide by minus n. This is just this doesn't do anything when you differentiate it, so it's fine. T plus 1 just differentiates to 1, so just ignore it. And then we end up with this here. We can, of course, put the 1 and 0 in. We do need to integrate this again, but I don't really actually have to, because the n's cancel, the minuses cancel, and then this is, as you'll notice, as was the plan, is just in. And then, of course, we just need to evaluate this, and we end up, it ends up not being too bad, right? We put in the 1, put in the 0, and everything just turns out as it should. So we've shown this thing here as well. Cool. Now we need to introduce that in is less than this thing here. Well, we have currently an equality between in plus 1 and we have an inequality relating the two. So if I just get rid of in plus 1 and replace it with a half in, I'm going to be making this whole side over here bigger, right? Because I'm going to replace it with something bigger than it is. So therefore, this whole side becomes bigger, and I'll get this inequality here. Of course, at this point, just move this over, and then there's a few different ways you could show this thing here from here. But I guess I don't know whether this was a sensible way of doing it. I said 2 to the power n was 2 to the power n minus 1 times 2, and I can cancel these divide by halves on both sides, and you kind of just get that. So that's that done as well. Cool. Now we're proving this thing here. Okay, so where on earth does a sum come from and a log 2? Like, how am I supposed to be using that? Okay, well, look at this nice and carefully. You've got a sum here, again, not sure where that's coming from, but 1 over r2 to the r. Now, the only thing we've got so far that looks like that is this thing here. So let's at least start with this thing here. Maybe rearrange for that thing there. So rearrange for it to be this. And actually just writing it like this immediately twigged it for me. Because if I take a sum of both sides, you're allowed to just take a sum of both sides up from wherever you want to wherever you want. If I do that, this looks like one of those methods of differences or series of differences or telescoping series that you often get both in A-level further maths and also in step questions. So this, just writing like this twigged it for me. Take the sum of both sides from 1 to n. And over here, when we do that, of course, you'll have I1 minus I2 plus I2 minus I3 and so on. And those I2s cancel, the I3s cancel, the I4s will cancel. You'll cancel everything except for the I1 and the in plus 1. So you'll end up with this statement here. This is exactly what we had over here, so that's fantastic. That's all good. Again, maybe just rearrange this for I1, because if we do that, all we have to do now is show that I1 is somehow log 2. How do we do that? Well, we just go back to the original integral and just evaluate I1, right? We replace all these things with 1s, these n's here. And of course, this just integrates to log of t plus 1. Put in 1, put in 0, get log of 2 minus log of 1. Log of 1 is 0, so it's just log of 2. And we end up with the thing that we're being asked to show. So yeah, really nice little thing there. And hence show, hence bound log 2 between 2/3 and 17 over 24. So this is where you want to use all the combinations of inequalities that you found so far, maybe with this result as well, since it has the log 2 in it, to try and bound from above and from below. So okay, firstly, what I decided to do was just throw in a number into this sum here. So if I just throw in n is 2, I get the sum from 1 to 2 is this, and then I3 at the end. Now, of course, this here is just 1 over 1 times 2 to the 1, which is 2. So that's 1 over 2 plus, and then you put in a 2, and you get 2 times 2 squared, which is 8. And you end up with this. Now, an eighth plus a half is 5/8, and that's sad because that's not the number I was looking for. I was looking for either a 2/3 or a 17/24. What I did at this point, and I didn't type this up, but I did 2/3 minus 5/8 to see whether I was kind of above or below it. And it turns essentially 2/3 is just ever so slightly bigger than 5/8, which smarter people than me would immediately know because this is 0.625 thinking about it, whereas this is 0.666. So this is slightly bigger. So what I decided to do was just go to the next one and hope that one more term, which ends up being a 24th, because it's 1 over 3 times 2 to the 8, which is 8. Sorry, 2 to the 3, which is 8. It's 24. And perfect, that gave me the 2/3. So this was kind of where I was going with that. Log 2 is 2/3 plus whatever I4 is. And now we just need to argue here that I4 is just some small, really small positive number, right? Because if it was, then that would make log 2 slightly bigger than 2/3. No, yes. Yeah, slightly bigger than 2/3, right? Because if we just don't add that very small positive number, then we will get log 2 is the same as 2/3, right? It's the same as 2/3 plus some very small number, so it's slightly bigger than 2/3. Now to do that, let's go back to my first slides here, where I was trying to argue stuff about this function here. Now, what I argued was it doesn't have a turning point, and it just goes in between 0 and 1, which is everything that I care about in this question, essentially. It just goes from 0 to a half. So this is a function that just rises slowly from 0 to a half in this range here. Now, if you power that up with lots of n's here, which is essentially all that's happening to get from here to here, that is not going to change, right? Because t is between 0 and 1, when you raise that power up, there's nothing funky going to happen. It's still just going to be a function that rises even slower now because you're raising a number less than 1 up to a higher power. But it's still just going to be a very slow rising function. It's not, and this is the key thing, it's never going to be negative, right? This is just a positive function between 0 and a half somewhere, being integrated, and so the area is positive, and the area is, of course, in. So in is always a positive number. So that's all I need, I think. I think I can argue that, and maybe write down some of the things that I said if you're in a step exam, but I, of course, have the microphone to use so I can cheat and just say things rather than write them. But of course, all that's really happening now is that we know IN, all of these INs, they're just some positive value, and they're getting smaller and smaller based on this inequality here. So I think I4 is something really small, probably, and therefore log of 2 is therefore a bit bigger than 2/3, because if I just remove that small thing, then I'll just get a side that's slightly smaller, and so therefore it's smaller than log 2. So that's this side of the inequality done. So now we need to try something a bit different to get the other bound up here. Can't just do the same thing again. We've got two things with inequalities in them, so they could be helpful. I decided to use this one because this one has the IN plus 1 in it, which is right here. So I decided to replace this IN plus 1 with a half IN, which is bigger than IN plus 1. So I'm going to make this entire side bigger, which therefore means log 2 is less than this thing here, which is fantastic. That's the right inequality symbol. And now what I could do is I could just try n equals 2 and evaluate I2 based on this integral, I guess. However, I don't think that's the easiest way to do. What you can do instead is you can notice this inequality is also going to be helpful. You can actually use both of them, because if you replace IN with this thing here, you're replacing it with something bigger than it is. So this entire side becomes bigger than it is, which means the log 2, this less than sign, will be preserved. You're just doing it twice, essentially. It's definitely going to be less than this. Not that it wasn't before, but now it for sure even more so is. And we can replace that with this thing here, which is fantastic, because now this is now easy for me. I can just put in n is 2 and hope that that's accurate enough for them. So just shove in a bunch of 2's into all these ends, evaluate this. This has two things coming out, right? It's the same as before, 1/2 and 1/8. This one also turns out to be an eighth, mostly because when you combine this 2 into here, it turns out to be the same term as this one here for whatever the last term is. So anyway, add these together, you get 3/4, which is not accurate enough for them. 3/4 is 18/24. So I know that I'm probably the one above where I should be. So now at this point, we do n equals 3, and we just put in the third one. We get these 1/24s, and that turns out to be the 17/24. So therefore, we've bounded both, and we have the entire question done. Thank you so much for watching, and I'll see you next time.